Hi, I'm John Niebuhr. I'm in the Department of Bioproducts and Biosystems Engineering here at the University of Minnesota. And I'm a domain scientist in the area of hydrology and water resources. And I'm very pleased. I feel very comfortable here because there's so many domain scientists that are in related areas. We've got agri-ecologists, we got aquatic ecologists, we got a number of hydrologists and so forth, geologists and so forth. And so it gives me pleasure to be able to sit here with them, as we interact with the computer scientists. I'm not going to take much time here. I just want to talk. We got a series of 4 presentations that are related to water resources, hydrology, water quality, and so forth. And one of the goals of I think that from my perspective is to have models that have explainability. I'm interested in the processes that actually generate the output, not just having a model that gives the output that is correct, that gives the correct answer, but we want to have models that give the correct answer for the right reasons. And this is a phrase from James Kirchner from Switzerland. I didn't make that up myself, but we want to have models that do the right thing for the right reasons and gives the right answers, not just black box models that give the right answer, because then you can't really trust them. So, our first presentation is going to be from Jacob Zwart. He's with the USGS, and he's going to talk about how much knowledge guidance is needed for these models.
Thanks, John. So I'm Jake Zwart, use he, him pronouns, data scientist at the U.S. Geological Survey. And, I don't think it's very controversial to say that science advances through empiricism and theory. It's kind of a reason why we're all here with KGML workshop. We observe the world, we touch it, feel it, see it, hear it, maybe throw things on the ground, use sensors to measure different things. And with all those observations, we form theories about how the world works. And then, we notice that we have gaps in our theories, and then that helps us know where and when to take new observations to help further refine those theories. And then in the age of big data and machine learning, we can actually allow algorithms to discover patterns about how the world works themselves. But Anuj pointed out great in his talk this morning that, despite having these very powerful tools, we still need empiricism and theory, and is the reason why we're here today about integrating science and knowledge into these machine learning models. But there's still this question about, okay, so we still need empiricism and theory to advance our science, but how much weight do we give one or the other? Do we give more weight to the algorithms, or do we give more weight to our theories? And I'm going to explore some of this question using aquatic sciences, and I think it's a great playground to explore some of these questions in knowledge-guided machine learning. And one reason is because we have a lot of great theory on aquatic sciences. We also have a lot of data in aquatic sciences. One thing that we're interested in learning or in predicting in aquatic sciences is water temperature. Water temperature governs a lot of biogeochemical processes. It impacts harmful algal blooms. It impacts fish species, among other things. And a good thing is that we know lake physics quite well. Here's an example of all the different processes that are encoded in equations in a process-based model. This one in particular, the general lake model, is highly used. It's kind of viewed as kind of like the state of the art of a process-based model. And I say that lakes physics is well known-ish because there are still some processes that we don't know very well. It might be kind of an empirically added portion of a lake physics model. And so there's still some room for improvement for our theory in lake physics. Water temperature is also widely measured. Each one of these dots across the continent or across the entire US is a location where water temperature has been measured at least once. There's literally hundreds of thousands of locations where water temperature has been measured. But most locations just have like one observation. And so this graph here, where the years of data on the x-axis and the amount of sites with this amount of data is on the y-axis, you can see that most sites, actually hundreds of thousands of sites, just have one point in time where they've had water temperature data. where there's this long tail of, maybe there's a few sites with 50 years of data, some that have even more than that, but it's very rare to have sites with lots and lots of data. And so when exploring some of these questions in KGML, we used one lake in particular that's been studied for over 100 years, and asked some of the questions around, okay, how much knowledge or how much weight do we give to our theory versus the data or empirical models. And so for when we're predicting lake temperature, we're comparing 3 different types of models that kind of represent these 2 camps. So one camp being, I guess, like the empirical only camp. So we're applying a deep learning model to make predictions of lake temperature. A theory only camp where we're applying this process-based model to predict lake temperature. And then this hybrid or a process-guided deep learning model where we are pre-training a deep learning model on process-based model output, and then also constraining that model with the law of conservation of energy. Okay, so now into the results. We train these models with various amounts of data. And so on the x-axis here, we varied the data that we gave it in training or calibration, anywhere from only 2 days worth of data. There's multiple points within the lake that we have observations. So it's not just 2 data points, it's more like maybe 20 to 40 data points, all the way out to 980 days worth of data. And here I'm just showing the performance. So accuracy being higher up on the y-axis of 2 of the different models, the empirical only model, so the deep learning model, and then the theory only model or the process-based model. We can see that the process-based model actually does pretty well when it doesn't have very much data to calibrate the model. This gives us trust in the model that it can perform or be generalizable to a bunch of different lakes. And an increase in performance when we calibrate it with more data points. You also see that it kind of tails off, like the performance doesn't increase as we give it lots and lots of data. And this kind of reflects the rigidity of some of these equations that we have or some of the parameters that we're calibrating the model with. On the other hand, the deep learning model, we didn't even show the performance with the 2 data points because it's really bad. But as we give it more and more data, we see that it quickly increases in performance and surpasses the process-based model when it has lots of data. And then when we apply the process-guided deep learning model, that has pre-training and the conservation of energy constraint, we can see that it actually outperforms at all data sparsity conditions. Even with just 2 days worth of data, the process-guided deep learning model is superior in performance compared to the other 2 models. Which is great for a KGML workshop. But, there's, this question, the deep learning model and the process-guided deep learning model are kind of converging when you get lots and lots of data. And it kind of, opens up this question that we had, what if we had more data? What if we had gave the model more data? And is there a point where actually the deep learning model without any theory or knowledge guidance actually surpasses in performance of the knowledge guided deep learning model? And so our group has been thinking about this and kind of comes up with these hypothetical predictability regimes where we might have accuracy on the y-axis and then these 3 different predictability regimes on the x-axis, where on the far left we might have a lot more theory than the data that we have. This could be for various reasons. Maybe we have really good theory and we're very confident in that. We have PDEs that describe the system very accurately. Or maybe we just don't have a lot of data. This middle part where, I think I was exploring this area in the previous example of predicting lake temperature, we're actually getting more data than we have that's compared to our theory. Our theory is pretty good, but, there's some missing components, or maybe there's something specific about a given lake that the data can actually, reveal, and some of these powerful algorithms can identify these patterns that are unique to the different specific systems. And then this third predictability regime, which, didn't explore in the last part, but maybe exists where we have way, way more data than the theory that we have. And that can be for various reasons. Maybe we just have tons of data, or maybe we just have really crappy theory. And also we don't know, if this exists for a bunch of different systems. Maybe the shape of these curves are looking different for, whatever you're trying to predict. And so there's, I think, a lot of exploration and opportunities for exploring the space. And so first, we just wanted to see, can we reproduce these patterns elsewhere? And so for the next example, I'm going to again explore this middle part where we think we have more data than we do have theory, and see if we can reproduce these curves. So it's not a huge leap in systems. We're still predicting water temperature, but we're applying and trying to predict stream temperature. And this is important for USGS in terms of thermal release decision support. We are now using this model that we're producing that I'm going to show in the next few slides as a forecast and delivering those forecasts to the New York City reservoir operators. And they use these forecasts to make decisions about releasing water or conserving water to supply for New York City drinking water supplies. And we're applying this in the Delaware River Basin. The Delaware River Basin, again, has lots of observations. Each one of these yellow points on the graph are different locations that have been observed or have water temperature observations. And the number of observations has grown through time. We have observations, I think the earliest one is in the late 1800s. This graph is only showing from the 1960s, but drastically the number of observations have increased in recent years. And for comparing different models for this system, we're actually not comparing to a process-based model. We're comparing or withholding or adding more different levels of process guidance to the model, and comparing those different levels of process guidance against each other. So the first level of process guidance that we're adding is temporal awareness. This may not seem like much of a knowledge guidance, but in environmental sciences, and especially stream temperature, what happened yesterday impacts what's happening today, or what your prediction is for today. And so we're using an LSTM in comparing that to an artificial neural network without any temporal awareness to see, how much more accurate can we make our model when we're giving it some temporal awareness. And the graph on the right shows that, yeah, we do improve our accuracy in predictions slightly, not a ton, but it is slightly improved with adding in temporal awareness. And then we're also adding in spatial awareness, because stream networks also are making a prediction at a given place in a stream is impacted by things that are happening upstream. So we're telling the model how close stream segment A is to B, how close stream segment C is to D and is to E. And it learns about how these different stream segments are related to each other. And when we add in the spatial awareness on top of the temporal awareness, we improve our accuracy even more. And finally, we're doing something similar that we did in the lake temperature prediction. We're pre-training on a process-based model output. And so we're showing it many, many thousands of examples of how we think the weather information should be translated into water information. And so it kind of learns the physics of the system. And when we add that on top of the temporal and spatial awareness, we get improved accuracy. And so similar to the lake example, we also varied the amount of training data that we gave these different models, anywhere from 0.1% of the amount of data available all the way up to 100% of the data available. And we can show that as we add more process guidance onto this deep learning model, we improve the accuracy, especially in the data sparse conditions. We also see that vanishing return as we give more and more data available to all these different models. And it looks fairly similar to our lake temperature prediction. So I would say pretty confidently that, yeah, we can produce some of these curves, at least in these two different systems. But we still haven't, the process guided deep learning or knowledge guided machine learning model is still outperforming across all data sparsity conditions. We haven't explored this space where we have more data than we have theory. And so now I'm going to show an example from a different part of the aquatic sciences. It's more about streamflow prediction. It probably rivals, streamflow data probably rivals the amount of temperature data that we have. In terms of abundance. And so it's also a good test case of where, we might have way more data than we have theory. And this graph is not from our group, it's from Freddie Kratzerts and others. And they're trying to predict streamflow, and specifically looking at the error in their error in their peak flow predictions. So when they're predicting floods. And And the x-axis is the return period of different floods, anywhere from very frequent flooding events, so one that would happen every 1 to 5 years, all the way to very rare events, so something that would happen every 100 years. And so the axes are swapped compared to what the previous figures that I was showing. So there's more data in the more frequent floods on the left side of this x-axis and less data on the far right. And then the more accurate is on the bottom rather than the top. So these axes are switched, but it's kind of the same concept. And they were comparing an LSTM to a knowledge guided LSTM, which was conserving mass. And so they have this mass conserving LSTM, and then comparing those to two different process-based models. And you can see that when they have lots of data, their LSTM is actually outperforming all the different models, even the process-guided deep learning model or their mass conserving LSTM. So it might be a evidence of, this is approaching, where we have lots and lots of data, and maybe the LSTM is just going to outperform any knowledge-guided deep learning models. Then we can look at the other end of the spectrum where they're trying to predict these very rare events or these 100-year flooding events. And you can see that the mass conserving LSTM and the LSTM are more comparable in their performance. And actually the process-based models are actually doing quite well and maybe outperforming some of the deep learning models. And so that kind of adds a little bit more evidence for, what we were seeing in the lake temperature and stream temperature and some of these data sparse conditions, some of these process-guided or process-based models or models that are rooted more in theory tend to outperform some of the purely data-driven approaches. And hopefully this is a softball up to the next set of talks, but one advantage of having this process guidance is the explainability. And what they're showing with this mass conserving LSTM is that you can actually have pretty good predictions of explainable states that you didn't even measure. And so this the blue line is a observation of the snow water equivalent at a given location that they were predicting for this mass conserving LSTM. And the yellow line is a sum of different cell states within that mass conserving LSTM, and see that they can mirror each other quite closely. And this is surprising because they didn't show the model any information about snow water equivalent. The model kind of figured out how to represent snow water equivalent within its cell states. And this has great opportunity for data assimilation or making predictions of something that you're not actually trying to make a prediction at by looking at these and investigating these cell states. Okay, so with that, I kind of showed a exploration of these hypothetical predictability regimes. I'm still not really convinced if this last predictability regime necessarily exists, where we have tons and tons of data. I kind of show an example of maybe that might be the case, but it also might be the case where we're not adding knowledge guidance in the right way, or maybe we just need to be more creative in adding our scientific knowledge to these deep learning models. So I'd be happy to take any questions or talk more about this third predictability regime. So thank you.
Any questions?
Thanks, Jake. That was terrific information. And just thinking back to a previous comment, maybe by Anuj or Xiaowei about Occam's razor. And, I wonder, as you add more and more complexity to the modeling environment, if you're essentially just adding, the equivalent of more parameters so that you get better predictions. So the complement to that, I guess, would be how well does it perform out of sample? How generalizable is it? Do you have any insights on that from these experiments?
Yeah, well, I guess the structure of the deep learning models stayed the same. So the number of parameters and everything kind of stayed the same across all those different levels of process guidance. But out of sample prediction actually was greatly improved when we added the process guidance to the models. And so we have, at least with the lake temperature prediction example, we did a training and testing of where we trained models on just winter and spring temperatures and then predicted on summer temperatures, which is very different in lakes, especially in the locations that we're predicting. And the process guided deep learning model picked it up right away and can make really good predictions even without seeing summertime data. So that gives some confidence to us in making those generalizable, and some evidence that the knowledge guidance or science guidance kind of helps with that generalizability question.
Thanks. So when I was looking at actually this plot exactly, it occurred to me that where you have the intermediate regime where the process guided deep learning outperforms everything in that, right? Yeah. I think early in your talk you described that the model you had inside there, the law was conservation of energy, right, which is fundamental. Whereas now, as you go to more and more data, that falls off, and it's deep learning alone takes over. So I wonder, is there the possibility of doing a study where you get into the the extreme data regime and systematically show that okay, you have the law of conservation of energy, fundamental, conservation of mass, also fundamental up to a point depending upon boundary conditions. But as you go to more and more data, you could have the possibility of adding more and more chemistry, for instance, where initially you have more general sort of chemical balance equations which are satisfied, but then you get more and more specific models, and you can have this kind of ordering of the important, the general, the generality of these models. Is there the possibility of doing that sort of study? Of course, the deep learning would also have to be very good. So maybe foundation models or something like that, right? Which can keep getting better. Mm-hmm. Sorry, long question.
Yeah, that'd be great. We haven't explored that yet. We are applying some of these models to different variables that would benefit from something like that: dissolved oxygen, salinity, carbon. A lot of these different variables that require an extension of some of those laws. So it's not a very satisfying answer, but yeah, I would agree that that's feasible. We'd love to do it, just haven't done it yet. And I would love to know if somebody else has done that already. So thanks.
Yeah, thank you so much. This is wonderful talk. I have the question about this particular slide. So I'm looking at this data is larger than theory, and then the deep learning is better than the process guided deep learning. Can you explain why that you think the deep learning will be better than the process guided deep learning in that process? Because typically that you can think of when you have additional knowledge, it probably will not improve the performance when you have a significant amount of data. And obviously it can also help reduce the noise and supposedly to be more robust in there. So just I guess why that you think deep learning will be better?
Yeah, I think it's in theory, process guided deep learning should always outperform or be very close to deep learning models. But in practice, we're probably either our theory is not perfect, or we're adding it in the wrong way. And I think there's a bunch of different experiments and stuff that we should be exploring to say, like, okay, here's our first cut at adding this process guidance or science guidance, but maybe for this system, we're not adding it in the right way. And so I think in that case, it's kind of a disconnect between like the theoretical applying the knowledge or science versus the actual putting it into practice. That's my take on it.
And if I could just add to that one, as Jake said, the knowledge that you're providing may not be perfect, and how could it be imperfect? Energy is always conserved, right? But for conservation of energy, you need to measure how much energy is coming in and how much energy is going out. You estimate that, and the estimation may not be correct. So you may be guiding your algorithm, your structure, using the conservation law is good, but the way the elements that are going into the energy components are not good. So basically you have to balance how much you know versus what you're injecting in. So these are very, very interesting questions, and I will give it back to you.
I think we need to move on. Hopefully we can cut a little bit out of the break and have some more conversation. But thank you, Jacob. All right.